more, I don't know, short unit before the end of the semester. It's actually going to get broken up into 2 different units. So if you look all the way down through these notes, you're going to see some things that we're not actually going to do this semester. We're going to look at, in this shorter unit, the math setup for second semester. So when we're looking at second semester math, we're going to do something called stoichiometry, which is based off of dimensional analysis. And we're going to learn how to round our answers for the math problems. That's called significant figures. So in today's video, we're going to look at SigFigs, or significant figures. In the video for tomorrow, we're going to look at the math of SigFig. So today we're going to get the rules down, and then after that we're going to look at the, I don't know, just simple math problems. I would say it's like 3rd to 5th grade math, where we're going to do 3 times 5, but then we're going to learn how to round that using the SigFigs. Friday we're going to look at dimensional analysis, or the day after that, with how to set up all of your math problems. And then next week, your final week, we have just a few more topics that we're going to talk about. We're going to get, again, set up for next semester. So we're going to have, molar mass, and we're going to have percent composition. And we'll use all of this when we come back in January. So these things will be on your next test. You will have a test next Friday, and you will also have these topics on your final. So what we need to talk about first is just measurement in the lab. I know if you've been at home, you have not measured anything in the lab yet, but if you're here on campus, you have measured things, and you've used a ruler or a graduated cylinder or a thermometer or something like that. And when you look at it, people just tend to drop off extra numbers. We're lazy people. We're humans. We want to do that. However, we have to look at the scale that is given to us, and we have to measure things as exact as possible. So when we're looking at the scale and trying to figure out what is there and how I'm measuring things, I have to figure out how many little tick marks are there and what all those little tick marks mean in order to measure things out. So we're going to measure things out, and we're going to have a unit of uncertainty. I would say that that's your guesstimate, where you're like, oh, it's somewhere in between 5 and 6, so maybe 5.5. Or maybe you're like between, I don't know, 1.2 and 1.3. Well, halfway in between that would be 1.25. So we have to use that digit of uncertainty where we're not quite sure. So up here I have it's a 4-sided meter stick, but there's different scales on it. In this one, it's really hard for you to see, but there's no numbers on it other than it says that it is 1 meter. So if we're measuring something with this, and when we're measuring it out, we're like, okay, well, this is, 100 centimeters total. Well, down here it's 0, and here it's 100. If something ends kind of like right here, I don't know, it's a little more than halfway. I don't know, maybe it's 60. That's a big estimate. I'm just guessing somewhere in between. So there's just one digit that you can read, and that's the 60 or the 70 or the 40 or something like that. But when I flip it around, now I have, ooh, it's upside down, sorry. Now I have tens on it. So down here you have the 10. On the other side you have the 0. So when you're measuring something this way, like let's say that I'm measuring a piece of paper, I put that piece of paper up here, I can read that it ended somewhere between 2 and 3, so that's 20 and 30 centimeters. Wherever it falls in between that range, that would be my digit of uncertainty. So if I'm somewhere between 2 and 3, maybe I'm at 26, maybe I'm at 25, whatever it is, but that digit of uncertainty is my last digit. So if I'm reading something right here, maybe I'm like, somewhere between 2 and 3, that's closer to the 3, 28. Again, that's an estimate. But when we get more numbers on the measurement tool, so if something ends, let me see if I can do this real quick. If something ends and I'm like between the 48 and the 49, so if I'm between the 48 and the 49, I do have one tick mark here that would be a half. So I know for sure if I'm reading something that's like right where my fingernail mark is, I know I'm at 48. The point is my digit of uncertainty. So point, I don't know, I'd probably say that that's 0.4. It's a little bit less than the half, so maybe 0.4, 0.3, but that digit of uncertainty is an estimated number. When we get a little bit more in depth, we have like more lines in between there. And the more lines that we have, the more digits we can have with your digit of uncertainty. So the better the measurement tool you have, the better you can measure things out. That is the whole basis of chemistry, because we actually cannot be more accurate than the scale that's given. So here with this scale that I have, this says 55 down here. This is 56. If I'm measuring something right here where that arrow is, I have to figure out what each of those lines mean. Well, this is 55.1, this is 55.2, this is 55.3, this is 55.4. So looking at this, I'm at 55.3. I know that that is somewhere between 0.3 and 0.4, so if I end right here, I would say that that's 55.33. Maybe some people would say 55.32. Maybe some people said 55.34. It's an estimated number. There's no real right or wrong for this last digit right here. But when you're reading that estimated number, we can put it there because we know that we're somewhere in that range of 0.3 to 0.4. That estimated number is going to help us to determine how well we can round our answers later. Because again, you cannot be more accurate than the measurement tool that you use. So you have to pull as many numbers off of a scale, whether it's a thermometer, graduated cylinder, ruler, whatever we're reading, you have to put all the digits. Now this one, your 13.1, this is 13.2. So this would be 13.11, 12, 13, 14, 15. My digit that I'm reading right here is somewhere between 13.15 and 13.16. So estimated in between there, if that's about half, it's about halfway between the two. So 13.158, 13.157, somewhere in that range would be your rate or your answer, sorry. But that last digit, the 8, that you're estimated, that is your digit of uncertainty. So when we're looking at all of these different things, we are measuring in the lab and putting that into math problems. And when we measure in the lab and we put it into math problems, we need to be as exact as we can, but not more exact in our math than we were with our measurements. So everything has to be reflective upon one another. So when we're looking at our answers, your calculator, when it gives you an answer, it gives you all these decimal places. All of those decimal places is a very, very, very exact answer. It's showing a lot of precision. We have to use your answer and the measurements, and they have to match up with one another. So we're going to have to take what your calculator says. You're going to have to round all of your answers off using something called significant figures. It's also called significant digits. Some people just say SigFigs. That's usually what I say. But SigFigs are just a way of rounding your math so that way your answer reflects the measurements that we do. And when we're going through this today, there are 5 rules that we're going to talk about. As we go through these 5 rules, everybody's like, why are we doing this? It doesn't make any sense. I get the rules, but why? Tomorrow we're going to apply it with the math. Today we're just going to look at numbers. And when we look at these numbers, we want to know, well, how many SigFigs are there? So if we look at something like 200, that's an estimated number. You have to have an estimated answer when you do the calculations. So with your 200 here, that actually only has 1 SigFig, and we're going to talk about why in a little bit. So if we have a cup of coffee at about 200 milliliters, we add another drop, 0.05 milliliters. Again, we still have about 200 milliliters. So when we're looking at our SigFigs, again, it's just a way of rounding your answers for what your calculator gives you, so we're not more precise than the measurements that we use to actually do the math. You do not use SigFigs for exact numbers. Like if I'm counting out 4 apples or 5 people, or if you're in your math classes, if you have Mr. Fesky, don't do this for Mr. Fesky. Round however he tells you to round. But with your SigFigs, We want to make sure that we are not more precise than the measurements that we are using for your math. So we're going to have to round a lot, going back to, I don't know, 5th grade, 3rd grade, I don't even remember when you guys rounded. My teacher used this little thing where it says 5 or more, let it soar, 4 or less, let it rest. All that means is if you have a digit that you're looking at to determine your rounding, so the next door neighbor, if it's 4 and under, it stays the same. However, if the next door neighbor that you're looking at is a 5 or bigger, it's going to go up a digit. So whatever you're rounding is going to go up or it's going to stay the same. So you're going to see me doing this quite a bit today, but I just wanted to kind of put that back in your brain because sometimes it has been a little while since you have rounded. Now, when we're looking at the numbers, sometimes you're going to have huge numbers, like 25.9874389, whatever. And then sometimes you're going to have decimal, like teeny tiny numbers, like 0.000058743112. If you have a number that is a decimal type number, you drop all the extra digits. Decimals, drop them off. If it's a big number, like if you have $25,614,000, you have to have those placeholder zeros there in order to maintain about the same number. So we're going to fill in placeholder zeros for big numbers. For tiny numbers, just drop away the extra numbers. And again, I'm going to do some examples. Normally, if you were here with the board, it would be a little easier, but I'm going to toggle all that in a little bit. Now, getting into your SigFig rules. You're looking at each digit individually. So this 235, I'm looking at the 2, I'm looking at the 3, I'm looking at the 5. The next number underneath that, I'm looking at the 6, the 3, the 5, the 8, the 8, the 8, the 1, the 4. I'm not looking at the number as a whole. I'm looking at each digit individually. And I want to know, is it significant in my measurements or is it a placeholder number? So when you're looking at your digits individually, anything that is not a 0, count it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, it counts automatically. So in this number, the 235, there are 3 SigFigs in that number. The 2, the 3, the 5, they all count because they're all a 1 through 9 number. In the next number down, you have the 635, sorry, I just dropped the meter stick, 888814. All of those numbers are all going to count. So this number has 9 SigFigs, or 9 significant digits. This number here, underneath it, has a decimal, but that doesn't matter. This decimal that you have here, you're looking at the 6, the 5, the 7, the 4, the 6, the 8, the 7. Everything's going to count, so that number has 7 SigFigs. Yes, 7. Underneath that, again, we have a decimal, but that doesn't matter. I'm looking at the 3, the 6, the 5, the 4, the 5. That number has 5 SigFigs. So look at each digit individually. If something is a digit 1 through 9, it counts. Your zeros are going to be your headaches, because sometimes they count and sometimes they don't. So we have to look at each digit or each 0 individually. And when you look at each 0 individually, you have to know these 3 rules on how to figure out if they count or not. Basically, we need to know, is it a placeholder or is it acting like a real number? The first one that counts as a real number is called a sandwich 0. I'm sure it has a more technical term than that, but that's just what I call it. A sandwich number acts like a digit that's 1 through 9. So like right here, the 5054. That 0 right there is acting like a real number. If we took it away, that number would completely change. So that 0 right there is a sandwich 0. It counts. So we count the 5, the 5 and the 4. That sandwich 0, because it's squished between a 5 and a 5, they count. So that one has 4 SigFigs. The next one, this would be like a turkey, avocado, bacon sandwich. So you have a 6 and an 8, those count. Those 3 zeros in between are sandwiched in between the 6 and the 8. Because they're sandwiched in between those numbers, they count. So that one has 5 SigFigs. This one here, it has several different sandwiches going on. These 2 are sandwiched between the 5 and the 6. These are sandwiched between the 6 and the 7. This is sandwiched between the 7 and the 8. So everything there counts. because they're all sandwiches. So we have 4, 8, 9, 10, if I counted that right. I believe that's 10. This one has a decimal there, but it doesn't matter. Those zeros are still sandwiched between a 2 and a 2. So because those are sandwiched in between, they all count. That one has 4. So far everything counts. Now we're going to get into the part where they do or don't. And these are leading zeros and trailing zeros. So the second rule, it says all zeros at the right of the number are significant only if the decimal is physically written in that number. If there is no decimal place written in that number, we're acting like it doesn't exist. Again, we're looking at digits, not the number themselves. So this one, the 523.000, there's a decimal place there. That decimal place shows accuracy and precision. So this is a very precise number. We were able to read something on a ruler or a balance or something like that, where it read out to 3 decimal places and it was dead on 523.000. That number has 6 SigFigs. These zeros count because there is a decimal place present. So zeros to the right count. If that decimal is present, they count. This one has a decimal as well, 0.2300. Again, that's a very precise number. Because it's such a precise number, these zeros count because there's a decimal place present, so that has 4 SigFigs. Now underneath that 500, there's no decimal place there. That's an estimated number. Somebody looked at something and said, it's about 500. They didn't really take the time to count it out, because had they counted it out, maybe they got 502, maybe they got 504, or however many. So because that's an estimated number, these zeros do not count. There's no decimal place physically written in that number, so there's only 1 SigFig in that number, and that's just the 5. Now underneath that, again, we're showing precision. We have 700.00. So somebody read something out, it has exactly 2 decimal places, so that number has 5 SigFigs. That 7, you're going to count that. And then all of the zeros to the right count because there's a decimal place present. So it doesn't matter where the decimal place is, if you have a decimal place, zeros to the right of the number, they all count. No decimal place? Now the last one. These zeros never count. These are the zeros at the beginning of the number. Zeros at the beginning of the number are just placeholders. They show how tiny the number is. So 0.023, that 0 right there, I don't know what the technical term is. Again, I'm not a math teacher. But that 0 right there, I always heard that as an accounting 0. It's to keep track of your decimal place. It's the same thing either way if you count or if you have it or not. So 0.23, you count the 2, you count the 3, that 0 doesn't count. All of these zeros, these are just placeholder zeros to show you how tiny that number is. These never count for SigFigs. They are just holding the place to show you how big it is. Just like the 500, those zeros didn't count because they were just showing how big it is. These zeros do not count because they're just showing how tiny it is. So, putting all of that together, zeros at the end of the number count only if there's a decimal place. Zeros at the beginning never count. And when I say at the beginning, I mean before the first zero number. Or if it's at the end, it's after the last non-zero number. So your first digit you count when you're cruising across from the left is your first 1 through 9 number. If there's no decimal place, the last one that you count is your last 1 through 9 digits. So kind of putting all of this together, I have some examples here, and then we'll kind of go from there with my document camera. So I'm going to flip this over real quick to that. I can't find it. There we go. And I'm going to use a pen. I am not very prepared today. I'm sorry. Let's see if I can find a pen. So this one, kind of putting all those rules together. 5.40. 0 is the end of a number count when there's a decimal place present. So I count the 5, the 4, the 0. That number has 3 SigFigs. The next one over here, that 0 does not count. It's necessary to write, but that 0 doesn't count because there is no decimal place written. So the 2 and the 1 are the only SigFigs that are there. So that one has 2. The next one, 0.00120. These zeros do not count. They just show you how tiny that number is. So in terms of measurement, they don't count. Zeros at the end of the number count if there's a decimal place present, which we have. So that one has 3. Just the 1, 2, 0. That 0 right there is a sandwich 0. That sandwich 0 counts, so this one has 4. These right here are sandwich zeros. They're sandwiched between this 3 and that 3. These zeros at the end count because we have a decimal place present. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. The next one, these zeros don't count. They just show how tiny it is. So in terms of SigFigs, 1, 0, 2 is just 3. 1,000, there's no decimal place present. So because there's no decimal place present, the only digit that we're counting is the 1. This one, that's a sandwich 0. Sandwiches always count like sandwiches. Zeros at the end of the number count when there's a decimal place present. So that one's 4. This one, that's a sandwich 0. That's a sandwich 0. Zeros at the end of a number count when we have a decimal place present. So everything counts here. So that one's 7. Zeros at the end of a number count when there's a decimal place present. So that one's 5. This one, these zeros don't count. They just show how tiny it is. Those are sandwiches. Those count. Zeros at the end of a number count when you have a decimal place present, which I have right there. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. This one, there's 3 variations on 700. This number has no decimal place present. These zeros are just showing you how large it is. It's showing scale. That one's just 1 because there's no decimal place present. This one, zeros at the end of a number count when you have a decimal place, so that one's 4. Getting even more precise, so they were able to measure this one further out. This one has 6 SigFigs because zeros at the end of a number count when there's a decimal place present. So when we're looking at the rules, I hope that kind of helped to clarify some things. I do have one more slide that I'm going to go through, and then we're going to pause, and we have a different video that we're going to do the rounding for your math. So looking at your SigFigs, you're going to see a lot of scientific notation in this class, especially second semester. With your scientific notation, they are very easy to figure out how many SigFigs are there. You ignore the times 10 to the 4th power. Doesn't matter what it would look like without the times 10 to the 4th. You just look at the 6.02. That one has 3 SigFigs. However many digits are before the times 10, that's how many SigFigs are there. This one, the 2.00, that one has 3. This one just has a 6 before the times 10 to the negative 14th. That one just has 1. This one, the 6.035558. All of those digits count, so that one has 7, if I'm reading that right. So it doesn't matter that it's times 10 to the 97th power, that there's like 92 zeros there. There wouldn't be a decimal place present, so that one, these numbers right here before the times 10 are the only ones that count. So I hope that helps. If you guys have any questions, make sure that you email me to ask. Have a good day.